Hey, good morning, good evening, wherever you are in the world. Thanks for joining today. So I do instrumentation, sensors, data acquisition, data analysis, and how do you use sensors and information in manufacturing and in healthcare. And there's a lot of overlaps between manufacturing and healthcare, whether it be in the hospital or at home. So the proliferation of sensors, the proliferation of technologies such as the cloud, somebody else's computer, the proliferation of computation, low-cost computation, the proliferation of new types of algorithms to make sense of the data. Right? So a lot of the excitement around machine learning is benefiting from the fact that we can collect more and more data. We have bigger and bigger computers sitting on somebody else's desk to be able to make sense of all of this. But the common thread that's really enabling a lot of thinking around digitalization, the use of augmented reality, immersive technologies, it's built on a solid foundation of automation, of process control, of instrumentation, of robotics. Ultimately, we have some machine or some process from which we're collecting data with some sensors. We're trying to convey that information to the human in the loop potentially. We have some data. We put that data into algorithms, whether they be signal processing algorithms that operate in a deterministic and very predictable way, or machine learning algorithms that require sort of statistics and learning of trends, and maybe if you rerun them, don't give you exactly the same results, but give you similar results. And then using the interpretation of that data to make actions and decisions. So I'm coming to you sort of fusing together a couple overlapping themes in manufacturing and in healthcare, but also representing a couple very interesting organizations on campus. Organizations that are designed to be a central facility for MIT, but also for the community. So the two sort of facilities that I represent, one of them is the Center for Clinical and Translational Research. That sits over in building E25, E23, and you see that here. Inside of there is the Center for Clinical and Translational Research, an open central shared facility staffed with clinicians, so nurses and doctors, and technologists that can help us mesh the research interest of when you're trying to do a human subjects study, where you're either looking at a new imaging device on a patient, or you're trying to see how somebody responds to a tilt table test when looking at new sensors to characterize their blood pressure or their heart rate. But it's an open facility that supports on-campus research, but it also supports off-campus research. So any industry member, and not even member, so anybody from the world around. It's a business. We can't make money. We're a nonprofit organization at MIT, but it's a set of resources that allow you to come and work with us in a way that is very unique to sort of the way that MIT researchers would engage with us to execute on their projects. Also, there's MIT.nano. MIT.nano sits in the heart of MIT, 200,000 square foot facility dedicated largely to nanofabrication, nanocharacterization. But also inside of MIT.nano is the Immersion lab. The Immersion lab is this big box theater that's populated with cameras, with sensors that allow us to capture motion as the person moves around. We have tens, if not hundreds, I think it's probably close to 100 of different types of headsets if people want to use either AR or VR technology in their classes or in the research that they're doing. Again, it's an open facility where we have staff and people that are experts in AR and VR and immersive technologies to help researchers on campus or off campus execute. And it's a phenomenal collection of capabilities that I think is unique in the world. There's a strong collaboration between what the Center for Clinical and Translational Research does and the Immersion Lab. And by the way, just a little bit of blatant advertising. We've just launched a new consortium for the Immersion Lab for companies that are very interested in sort of getting an even deeper dive into the things that we're doing. So first, let's start with if these walls could talk, an inside look at ambient sensing. Ambient sensing, what I define that to be is a camera immersed in the world is an ambient sensor. It's not making contact with me. I didn't have to remember to put it on in the morning. But there are many types of ambient sensors. And I'll just go through what some of the capabilities are first in the Immersion Lab. The Immersion Lab, I think of it as it's an instrument into which, instead of a microscope into which you put your cell, it's a room into which you put your human. And from that, you can measure them with cameras, with wireless sensors, whether they be RF radar sensors or sensors that you're putting on your body for contact, that allow us to capture the full state of the person, physiological responses as they're moving around. And also a whole slew of different technologies for them presenting that information. The Immersion Lab is in some ways the data interface to MIT.nano. MIT.nano, we need to do training before we put people into the fab. So how do you get on the tools and experience what that use of the etching machine or the cutting machine or the bonding machine would do? How do you operate it before you go in and get bunny suited up and go into the fab? Or if I'm generating a lot of data from a scanning electron microscope and I want to blow that data up to something that instead of being on the screen is a three-dimensional representation of a cell that I want to be able to dig into and fly into and experience and do what I'm doing, gesticulate and navigate through it. So being able to understand how people are moving, to capture their natural interaction with data or with virtual worlds. So let me tell you a story that connects some interesting things between dance and motion, just to strike a little bit about some of these interesting connections. So here is a video sequence captured in the Immersion Lab, where we see the MIT's baseball coach who's fully clothed, and then a person that he's training to become a better pitcher that has shirt off and wearing markers on his body to make it a little easier for the ambient sensors of the camera to see him. These cameras are distributed all around the room. You can see them represented here, and they're above the screen here. But from all those 32 cameras in the world, we're able to track all these points in 3D and understand the trajectories of how people are moving. Okay, so it's biomechanics, understanding how people are moving around. But hand in hand with that, wearing sensors, wirelessly telemetrying the data that's coming from the electrical signals of muscle activity at the rotator cuff, or the accelerometer on the foot to know when you're making contact and how your leg is moving around, or sensors, wireless sensors in your shoe to understand what's the load that you're applying as you're distributing and pitching this baseball. So this full visibility, gives the coach now a lot better insight into what you're doing and able to guide you, say, okay, I notice how you're not coming off your back foot at the right time, and I can see that not just from how I'm watching you, but from the data. So one of the interesting things that we've done, this was actually on a documentary in Canada. This is a professional dancer and her coach on the side. And he's trying to convey to her how to perform a particular move. It has sort of guide her through becoming a better motion expert. That's what dancers are, motion experts. So what you're watching is she's wearing a augmented reality headset. And if you go back here, let's see, right in, where is it? Let's see, right there we go. So you see some marks that are taped onto her back. And you also, as the video plays, you see these points floating around in space. So what she's experiencing while she's dancing and moving around, she's seeing herself from the sort of the bird's eye view from behind her. And so now when the coach is trying to convey to her, move this way, do this, he has a better time, easier time to do that, because right now he'll try to describe it in words or touch her shoulder to say, move like this, do this. This provides both the visual input to the coach and to the dancer of what she's doing, and superimposing that on herself in the world. Okay, so that's just a little bit of, okay, you have capabilities that allow us to capture motion, capture physiological signals that can be used for better training of motion experts. And motion experts include dancers, but they also include people on the factory floor, as we'll get to that. Now a little bit more about, I'll call it ambient measurements, and trying to celebrate some recent doctoral work from Katie Hom, now Dr. Katie Hom, who just defended some of this work last week. So you're certainly familiar post-COVID with the use of thermal cameras to measure temperature. You've probably heard of work from Dina Katabi at MIT using Wi-Fi signals, trying to understand how people move around in the world in their homes. Here's a video of somebody breathing through a mask, thermal camera. We can get their temperature, but we also, interestingly, can see how they're breathing. We see the respiration coming through the mask. This is one example of an ambient sensor. Another example of an ambient sensor would be the sort of thing that the speed traps that may be out there. If you take a continuous wave Doppler signal, bounce it off of a person. You're a mirror to a radar signal. So as your body moves, whether you be walking through space or as you're breathing or your heart is beating, those motions are producing motions on your body, on your torso, on your neck. And a radar signal bouncing off of you is going to be modulated by that. I can detect those signals, and I can look at the frequency content of how you as a mirror are vibrating, and I can pick up the frequency peaks, the oscillatory motion of you as a mirror to radar that corresponds to you breathing or corresponds to your heart rate. I can now have multiple people in a room where there's a radar sort of sensor of a couple or one, and I can detect how many people there are. I can track the respiration rate and see what they're doing, or heart rate and respiration rate, and see how, in a non-contact way, what they're doing. One of the interesting applications, one of the funding sources for this, is a large home builder. They would like to deploy ambient sensors into the houses that they sell, and they provide a continuous service for emergency intervention if I've fallen and I can't get up, but sort of as a service consistent throughout all the homes that are delivered to detect when somebody has potentially had an event, right? Not to diagnose anything, but to detect when somebody has potentially had a significant change in their heart rate or their respiration rate. Significant changes not being a sort of a diagnosis, but an indication that that person should be called and do a health check. We deployed some of these technologies on campus during the pandemic. Some of our students developed a kiosk as a future alternative to when you go to the doctor. The first thing that the staff will do, the clinical staff, take your blood pressure, your temperature, your heart rate, respiration rate. Wouldn't it be interesting? I think there's some good use cases, both in a clinical environment or on campus, where I go to the doctor, I sit down after I've relaxed and gotten over the fact that I'm at the doctor's office, but in the act of sitting there in the waiting room, in a non-contact way, I'm getting my blood pressure, my temperature, my heart rate, and potentially streamlining the process, potentially sort of really changing the way that healthcare can be deployed in the clinic in different environments, and helping the clinician, reducing the time and complexity and the burden of getting the SEBA data from the individual. Now, the vital signs that I've spoken about, heart rate, respiration rate, temperature, those are your standard vitals. Right? Those are the things you think about when these are the standard numbers that people are going to acquire when talking about your state of health. Another really important one that it's hard to get clinically, but that if it were able to be acquired in a convenient and easy way, is motion. Particularly if you're suffering from a neurocognitive disease, how you're walking, your gait, whether you have a limp, or the changing pattern of your gait over time as there's potential neurocognitive decline, is indicative of state of disease, of progression. Now, typically, if you wanted to characterize your gait and motion, you would come to a gait lab or a biomechanics lab, not dissimilar from the Immersion lab. You'd probably walk on a treadmill. We'd track your motion. We'd be observing you. But you're under observation. There's ample evidence that says that you respond differently when you know you're being observed. You've kind of come to this pristine environment that only exists in sort of a few places. Now, there are certainly biomechanics labs in the hospitals around Boston, but it's not a tool, keep hitting this thing, it's not a tool that's available to the general practitioner. Although motion as a signal is extremely important. You know if you're getting up and you're feeling achy, it's the first indication that something's maybe not right. Maybe you didn't sleep well, but there may be some other underlying diseases. So what we want to try to do is, how do we get motion out of the Immersion lab? How do we get it out of the biomechanics suite? How do we get it into the home? So the work that Katie did for her doctoral thesis is asking that question around gait. Where you are walking in the home is on the floor. So how do we instrument the floor to potentially get some numbers, get some data that would tell us something about how somebody's moving? And in particular, she puts accelerometers on the corner of the floor. And as you walk around, those accelerometers pick up you vibrating, or your floor moving around, or the sound that propagates, the acceleration that propagates through the floor. Now, she did start this work during the pandemic, and so she instrumented her apartment, turned their apartment into a lab, which was great. This is just one of the first videos of some of the data that she was collecting. So the black things are accelerometers retrofitted to the floor. taped out markers just to have a general sense of where she's walking, and gets data that doesn't look dissimilar from this. So here, if I zoom in for a moment, this is what the acceleration signal looks like from one accelerometer in the corner, whether you're wearing barefoot or shoe strike. If I'm walking around in the home, often I'll get up, walk a few steps, stop, do something, come back. I don't have a lot of long walking in the house typically, so I need to collect a lot of the short episodic walks that I'll do between the bed and the bath or across the living room. And what we're looking at here is four episodic walking cycles of somebody walking through their living space. And we don't know if they started with their left foot or the right foot. We don't know which of these spikes recede at one accelerometer corresponds to which foot. But if we just start to look at the statistics of that data, if we say, well, left, right, right, left, there's a timing between. And if we just start to look at the time difference between the subsequent footfalls, if you're walking in a balanced way, you expect left, right, right, left to be the same. If you have a limp, you expect it to be a little bit longer on one side than the other. So the first work that she put out was just demonstrating with a sort of a small pilot study that we're able to use step time, the statistics of step time, to evaluate and quantify the severity of limp. And then the further work is, well, limp in step time is one thing. The data collection, the experiment was one of the other important things for gait is how hard you're walking. So if you have a heavy foot, or if the force that you're putting on one foot is very different than the other, that sort of reaction force as you're walking is also very powerful. So can we learn a way to, from the acceleration signals, estimate what that ground reaction force is? To train to answer and ask that question, put on something that provides the ground truth data, so accelerometers and inertial measurement units on the leg, so we can measure acceleration or measure that reaction force, and then train a network or a series of learners or of regressors to relate the signals that we get from the accelerometers to the ground truth, then take the ground truth away, measure the acceleration signals, and predict what we think that ground reaction force is. And as it turns out, if you sort of look at that in sort of summary, as I'm walking, I'm stepping, each one of the small points on this screen is saying, well, here is the real tibial acceleration as measured with the ground truth, and here is what the algorithm predicted. Each one of the blue points, you can see any one of them on average is not very good. So the real acceleration was 1.5 newtons or meters per second, and the predicted was something very different. But on average, as you're walking around the home during the day, the average of those noisy measurements is actually very good at predicting what the real tibial acceleration is. So another gait parameter that has been learned to be extracted from that acceleration data. So we're applying that now with sort of in the home, where we can have both sensors in the floor, sensors in the ceiling for heart rate and respiration rate, and sensors and the artifacts and the things that you interact with, the door, the handles, so grip strength. Now, let's connect this a little bit to the workplace in a slightly sort of interesting way. While we were studying dancers, motion experts, who are good at performing efficient motion, we observed, we weren't the first to observe this, but it's not as commonly known as it should be, that there's an efficient way of doing motion that I'll say is smooth in some sense. So if you become really good at moving, there's very little uncertainty in your motion, and you do it in a very elegant and smooth way. And what that means technologically is if I put an accelerometer on a motion expert, somebody that knows how to sort of relax and sort of connect everything through their body as they move in a very holistic way. So not that I'm trying to be a mystic, but from the technical perspective, if I collect that acceleration data from somebody that's not a trained motion expert, and I compare those signatures to how they move with a trained motion expert, we observe these things that we've called wobbles, or shaking. You don't observe it, you can't see it, you don't feel it. But if you put the accelerometer on there, you can see it. We're hoping that we can see it with some higher resolution video. But the unique observation is, if I'm uncertain, or if I'm not being as energy efficient in my motion as I could be, these wobbles show up. So, okay, fast forward. Now we're in collaboration with the Fraunhofer and through the MIT Portugal program, evaluating, well, how do we use that observation on the factory floor? So let's instrument an assembly line worker as they're doing an assembly task. collect their data, both camera data as they're moving around and accelerometers into the Fitbits and the Apple Watches of the world. And we can observe, these should be motion experts. These are people that are doing a repetitive task that we would like them to learn how to efficiently do this so they don't fatigue themselves. So this wobble is indeed observed. And what's interesting, now if you take this data and observe the experienced worker, somebody that's been doing this for a long time, that has presumably become more efficient in learning how to do it, to the inexperienced worker, the number of wobbles in the inexperienced worker is a lot higher. So there's a metric here that allows us to either say, hey, well, okay, you could benefit from additional training, or if in observing the experienced worker as they fatigue, we do observe that the number of wobbles increases as you get more tired and become less efficient in how you move. Okay, so motion has been very interesting in understanding just general health, but we now have some interesting signals that we can apply in the factory floor potentially to help in training and sort of ergonomic work design and sort of fundamentally worker safety. Okay, so let me transition a little bit. Both when we talk about manufacturing data or if we talk about medical data, one of the big questions, as it should be, is how do we do all this data analysis in a secure way? One of the common challenges I'm sure many of you experience is that you probably don't have a large enough staff for data analytics. You have a lot of data, you have a lot of data opportunity, and you'd maybe like to outsource some of your data analytics. And if you're going to do that, you want to have the contractual business relationships that allow you to share your data, but you'd also like it to be just fundamentally safe in some way. Like we want to do all this machine learning, make it part of the natural ecosystem of collaboration, but we have to be concerned with security and privacy. So this concept of locked learning builds on certainly the proliferation of data in manufacturing, the proliferation of data in medicine, but in particular, what this technique that I just want to share with you so you have it in your mind, a technique called homomorphic encryption. In a nutshell, what it allows is complete end-to-end encryption of your data. The example that I like to give is I have two numbers. I have 2 and 3. And you know how to add. This wonderful algorithm, I have no idea how to do it, but you know how to add. And so I need to outsource my adding. So I give you the 2 and I give you the 3. I give it to you encrypted. Typically, you would have to decrypt it, run it through your adding algorithm, re-encrypt it, and send it back to me. What homomorphic encryption allows you to do, I send you my encrypted 2, I send you my encrypted 3. You don't know, nor do you ever need to know that they are a 2 and a 3. You're going to add them together. You're going to add 2 encrypted numbers without ever putting them into plain text. You're going to get a new number that, well, we know secretly it's 5, right? Because you know how to add. And then you're going to send it back to me, but you didn't know it was 5. I get it back finally, and I can then decrypt it and know that it's a 5. So it's this concept of complete end-to-end. So it requires new ways of sort of modifying some algorithms. It requires additional computation. There's been a lot of DARPA investment. Now Microsoft and Samsung are releasing both chips and libraries to do this thing called homomorphic encryption. This is the example that I like to use. So you start with the 2 and 3. I encrypt it. I send it to you. You know how to add. You send it back. I get, in all honesty, I get something that's a little bit different than a 5. Part of the encryption mechanism is adding a little bit of a noise. But I get something that, to the significant figures that I need it, is a 5. Now, okay, that's as the technology. One of our hypotheses is indeed, as I suggested, that there's a need to outsource, or at least make it easier to choose to outsource your data analytics if you don't have sufficient staff internally. So the paper that we wrote, the first paper that we wrote on this, was sort of the use case of a small organization that makes a product of fiber. And the machinery that they use includes rotating pieces of equipment. And when you look at the condition monitoring or preventative health maintenance or predictive monitoring for in the manufacturing context, a lot of things that go wrong are rotating pieces of machinery whose bearings die, whose oil wears out. And what you're looking for is shifts in how that machinery is moving, right? Changes in how the frequency response. If I have a bearing that's out of whack, it's no longer, I'm going down the road, I'm going down, if my wheel's out of alignment, right, I'm shaking, right? So I want to detect that shaking. So what we've demonstrated and what we developed is a homomorphically encrypted FFT, the Fourier transform, the workhorse of many types of signal processing, and then deployed that and used that as a test case to say, well, I had this vibration data coming from a machine, I encrypt it, I send it out, somebody else that knows how to do the encrypted version of the FFT does all the analysis, does the thresholding, and says, well, your frequency peaks have shifted, we think that you have a problem, so you can outsource now, create a business model where another organization can help you with the analytics where you've never had to expose to them that fundamental underlying data. So the paper, if you're really interested, you can drill down into this homomorphic encryption as a secure preventative health maintenance outsourcing solution for small and medium manufacturing enterprises. Wouldn't have to just be small, can certainly be big. And sort of the full story, again, is data encrypted, perform analysis on the encrypted data, and send the encrypted answers back so that it can make then decisions. The other sort of the current progress, or the current project that we're working on applied to that, just briefly, conceptually is sort of still using homomorphic encryption, and what we're doing is trying to develop a predictive monitor for the health of a piece of equipment. So here we take all the IoT data, all the sensor data coming from a packaging machine, and we want to relate that IoT data to wear on the blade. So basically it's a decision tree algorithm where we do an experiment where we have over a period of 12 months, we run the machine until it wears out or until the blade wears out. And then we have a surrogate sensor. We have, in that experiment, we have age of operation over a 12-month period as a surrogate for the wear of the blade. We started the blade brand new, run the machine until the blade wears out. And so there's no wear sensor except for the surrogate of age. But then we train a network to say, given all this IoT data and the sensor data and the control system data that had to respond to whatever the changes were, can we predict wear? And as it turns out, the answer is indeed yes. We're able to predict wear. If we're able to predict wear within a 2-month window, that's sufficient for making decisions to take your machine down, to do the preventative health maintenance. And so we're deploying this now through a mechanism through the lens and through the use of homomorphic encryption. Okay, so let me, in rapid fire, I'm going to go skip to right here. Okay, so there's just a lot of really phenomenal opportunity sort of playing in this space between manufacturing and healthcare and the application of sensory data for humans, the use of data and visualization for training and display. And I just, in the last few minutes, want to share some of the straddling back and forth that we do in developing technologies for imaging or for characterization that benefit from things such as SLAM, simultaneous localization and mapping, the thing that Google does when they drive their cars through the world to create Street View, or the thing that self-driving cars do to self-navigate the world, to say, as I'm driving through the world, I want to simultaneously, if I have a single camera, or if even I have 2 cameras, if I don't have a map of the world, while I'm moving through the world, I need to develop a map and figure out where I am. So we're applying that to manufacturing and medical applications. In particular, I'll first start with the medical. Here we take the application spaces in ultrasound. Ultrasound typically being a sort of a great technology, a great imaging modality that is quick and easy, non-ionizing, but it suffers from user variability, and you're getting a single slice. So as we slide around the body, or we move an ultrasound probe over the body, if I can know how I'm moving around, how the probe is moving around in 3 space relative to the body, I can acquire subsequent images, know where my probe is moving relative to me, and stitch together those images. So I add cameras and inertial sensors to the outside of the probe. As I fly that probe around, as I move it over the body, I'm estimating where I am. I'm estimating and I'm creating a map of the world, which is shown on the left. And I can stitch together the ultrasound imagery so that fundamentally I can then have a volume of data similar to what I would get with MR or CT. And I can extract now dimensionally accurate volumes. Melinda Chen, different doctoral student who also defended now 2 weeks ago, for her doctoral work, expanded this concept to looking at needs in the liver, where in particular, if you're trying to image the liver, and so apply this concept if I can fly around the world and the world being the body and stitch together volumes of an organ. The liver is such that you can't, with one location, get a full image of the organ. I need to, if I want to see the full liver, I can X-ray or MR so I can see through the bones. But if I want to do with ultrasound, I do intercostal through the ribs at some window. I do under the ribs. I need to stitch together different views of the liver at different locations. Again, building on the technology of, okay, I need to, any one view, any one place where I put down the probe before I picked it up, I construct these volumes. And then I need to stitch them together to form a full volume. And she demonstrated the ability to do that using a combination of this idea of SLAM, or cameras to the outside of the world, and also applying sort of deformation metrics on the features, in this case the vasculature that is seen in the liver. Now, real quick, let's make the connection to how we're doing that, how we're using that in manufacturing. So the way that we're using that in manufacturing, say for example, I'm trying to analyze do a non-destructive test of a section of fuselage or a piece of material, right? So I have structures and features, and I have a high resolution either X-ray system or imaging system where I see both surface and in-surface, and I want to scan over that surface in an efficient way and stitch together the full volume or the full surface. So the same technologies now of flying through the world, stitching together lower resolution data or smaller view data to larger data to give you that view is enabled by the same thing. Okay, so I think that's at the time. I'm going to do one more. I'll do over one more, real quick one. Just as I'd like to celebrate this one in the work of Dr. Sean Zhang. I'll start with the manufacturing application first. There's a long history of using light to generate sound. If you shine a laser beam on a source, on a piece of material, a pulsed laser beam, that laser beam will very locally heat up the material and create a sound wave. That sound wave will propagate as sound, bounce off a media, or interfaces, come back, and if you use a continuous wave interferometer, another light bouncing on the surface, you can detect those vibrations. So there's a long history. In this case, we developed a system using non-contact lasers, or lasers for non-contact, a pulse laser to generate sound, a continuous laser to detect sound, to monitor the temperature of silicon wafers undergoing rapid thermal processes. As the sound travels through the wafer, its temperature impacts the elastic constants, impacts how the sound travels, and so I can analyze the data and estimate temperature. But then recently, 2 years ago now, right before the pandemic, with collaborators at Lincoln Lab, Sean, as his doctoral work, sort of translated this now into the clinical space, where using an eye and skin safe laser, pulse laser shining on the body, sliding back and forth with a continuous wave interferometer sliding back and forth over top of it, able to collect the data that from a meter away from the person is an ultrasound image of the person. It's analogous, roughly, there's some different resolutions, other sort of caveats here, but side-to-side comparison of what you would get with an ultrasound probe placed on, in this case, the arm, and we see the skin, we see the muscle fascia, we see the bone boundary, analogous to what we would see if we actually had to bring a probe in contact. Okay, so with that, just wanted to tell a little bit of a couple different case examples between manufacturing and healthcare. Welcome the conversation and questions, so thank you. Should I take the questions on the screen first? Okay. So the question is, general purpose homomorphic encryption seems some way off. Are domain-specific homomorphic encryption, such as HFFT as stepping stone, what other building blocks seem likely? So it depends on what sector you're talking about. Homomorphic encryption has been used, for example, I know in South Korea, they've been using it to safely share demographic data, population data. And when you're making decisions at the policy level, you don't need to be as fast as if you're trying to make a decision on the factory floor. So the knock against homomorphic encryption, the way that I'm give you this encrypted 2 or this encrypted 3, I make the number bigger, right? I'm projecting it into a higher dimensional space. I'm sort of multiplying it by a bunch of coefficients, a polynomial. And so the act of a 3 that's a scalar becomes now a vector of parameters. And so the computation cost is expensive. And so the drive right now, the reason that it's so exciting that Microsoft is coming up with new libraries and Samsung's coming out with new processing is you need that sort of specialized set of tools deployed to make it faster, right? So if you want to do this on the factory floor for real-time decisions. So there are places, I mean, general purpose in the sense that you don't have to ask the question, well, what are the constraints? It's not there yet. It works well in some places, but for real-time control, there's still work that has to happen for homomorphic encryption to be fast enough in all the types of computation that you'd want to do. Okay. Awesome. Do we take questions here? So if people have questions, so we should encourage people to raise hands or focus on there? Okay. As someone forging the future of remote monitoring, are there any privacy principles or policies you think are important for the future? Yes, many. The reason we work in and also in sort of in addition to the data analytics and to the security piece, it's the pervasive, it's the right question, it's the right societal question. Your data. I come at this when you think about viewing human subjects. Right? There's a whole mechanism to go through to make sure that the human subjects tests that you're doing are fundamentally safe and fundamentally observant and conscious and fully informing the subject how their data is going to be used. That's when you're doing a study, but the same principle should apply when you're deploying a product. One of the reasons, for example, that this home builder that wants to deploy radar into the home, we could sort of probably fast solve some of the problems if we deployed cameras. But cameras have a higher likelihood of a privacy violation, right? So from a privacy and security perspective, we don't want the cameras in the home with that data streaming out to a third party. But it seems to be a little bit more acceptable, the lower resolution information of what you get with, say, radar and or sound. Fundamental, I think there is some important questions around individuals should be able to monetize their data in the future. There are certainly, I'm drawing a blank on the name, I apologize, but there are some really good researchers at MIT that are asking the question, well, what would it mean? What would the economy of data sharing look like? So thinking about how could people choose to potentially monetize in the future from the data that they share? But fundamentally, yes, I mean, the privacy issues are fundamental, and I don't have a golden fix for them, but certainly taking one piece out of the problem with techniques in homomorphic encryption. Okay. Is there another? I see a 6 vote there. How's that one? How accessible is this technology to bring it into the mainstream healthcare? Does it require significant training for health workers? Depending on the technology. We are actually, I think, extremely, based on the work that Katie did for the floor sensing, is what I'm picking on first. As an approach, the ease with which an organization could stand up and actually make a product or a set of product offerings around that, we haven't done the full market analysis of what would it look like, but in terms of the maturity of the technology and her doctoral work, got it to a phenomenal level where not only can we look at this, characterize gait, characterize the tibial acceleration, but she can also do that for multiple people in the room. Disambiguate multiple people walking around, and not only that, but identify when people are coming in. So there's a lot of really, there's technology that's ready to at least sort of take that next step. We need to sort of the organization, either a startup company or a big company that would like to push on that. That's sort of one aspect. Things like homomorphic encryption, mainstream is a little bit off. Things like using accelerometers or sort of the Fitbits on the factory floor. That technology is ready. I think there's some interesting policy questions around how willing are the factory workers or any workers willing to be monitored and observed. There's a lot of conversation around now in terms of the ability in the Zoom era and the remote working era. There's a lot of tools where employers can actually know in detail what people are doing all the time. Putting things on the person, that makes it maybe even a little bit more risky. But so I think there's pieces of technology that are ready, but some of the policy things still need to be addressed. Okay. In a real-life situation, what data architecture pipeline do you need for the privacy-protected machine maintenance service if you want to make it available for analysis? So data architecture pipeline you need. So you would need to collect the data, right? You need accelerometers or sensors that can collect the data from the piece of rotating machinery. The data pipe, whether you're doing it with homomorphic encryption, we do a lot of work with manufacturers and say, well, we want your production data. Or we're trying to learn from production data for either identifying sort of quality drifts, improve process control. And to a T, it's like, oh yeah, we have the data, we've saved it, we have the data. And then the act of actually getting it out of the database, figuring out how to get it where it is, and then working that back through. Those data pipes, homomorphic encryption or otherwise, you need the data engineers to sort of manage that. But you need to be able to get the data from the machine out encrypted, and the encryption doesn't take long, so that's just a sort of a simple set of CPUs, and then made available. So whoever asked the question, happy if you ping me on LinkedIn or other to follow up with more details. Okay, nice work. When adopting various machine visions, there are still tons of limits, especially for inspecting the unseen parts. Would your approach be the way of overcoming it? Maybe. Certainly vibration signatures, if that's the one you're referring to, vibration is a sort of a great way to characterize the state of the machine. Slides that I skipped over that I'm sure there's some ILP talks of me in the past archived where I talk about video instrumentation. So we've done a lot of work where the conventional use of machine vision on the factory floor is I had this bottle coming down the conveyor belt. I take a picture of it. I look at the cap. Is it correct? Is the height of fill correct? And I can make pass-fail quality decisions based on a single image. We do a lot of work where it's not a single image to tell you something about the quality of the part of the process. It's the motion. So if you are a robotic system and you're trying to follow a particular trajectory, or if you're welding, and it's not just the final inspection of the weld, but you want to monitor the weld as it's going on. And yeah, I had this molten, amorphous, squishy, fluidic thing. I can see it. I can see when it's happening. There's not a single image that I could acquire to say good or bad. I need to have a video. And then the question is, well, how do I in real time analyze video? So we've done a lot of work in using video for that type of question, for things that require that temporal spatial observation. What regulatory challenges do you expect around privacy-preserving technologies, techniques such as homomorphic encryption and others? How cost-effective can this be implemented at the edge? So it's not cost-effective at the edge just yet, right, because the libraries and the processes are coming. There's massive investment happening in it. So at the edge on the factory floor, we're probably not there yet. Things that are at a days of if you really want to do big data, and I guess the other thing, at the edge, maybe the downside of the example I gave with outsourcing it is that that's not real time. The act of outsourcing is there's the time with sort of getting it to the place where you've outsourced it. There's the analysis that's coming back. It's not a real time thing, but you're looking for drift. You're looking for drift over time scales of days or weeks. And in that time scale, it's fast enough. But if you really want to do it at the edge where you need sort of a decision or some knowledge happening on the second level, that's not there yet. I'm not sure you would need that, because if you're needing at that time scale, that's some learning you probably want to have in-house instead of outsourcing something that requires a lot more data and a lot more computation. Okay, certainly interesting. What else do we need to consider when utilizing the presented technologies in order to lead better decision-making and behavioral changes within a corporation? I guess I tried to cover a bunch of different technologies. Yeah, there's certainly this morning before this class, or before this I was in class, teaching the Toyota production system. And I introduced the Toyota production system through the lens of the class I teach is in manufacturing systems. And we teach a lot about discrete event simulating and how to design the tools, the simulation and numerical tools to predict what a factory is going to do and the impact of different buffers. And so we teach the engineering concepts of how to design and lead change within the organization. And effectively, TPS is the cultural aspect of manifesting, implementing change. And so I would argue that the organizational sort of needs is sort of inoculating your staff with the opportunities with whatever technology you're choosing and sort of communicating that well. I think that's one of the big challenges that I see, at least as we work with companies trying to deploy machine learning techniques. A lot of the reason they come and collaborate with us is that we have a particular problem that we want to solve. Okay, here's this data. We want to make a better controller for this process, or we want to detect quality. Oh yeah, but by the way, what I really want is to make sure that my staff are experiencing the process that you're following, developing those techniques. And it's not so much the technique that we end up using, whether it be a regression tree or a support vector machine. It's sort of the thinking around how to sort of simultaneously be thinking about the physics, the manufacturing, and the data analytics and that process. So speaking that dual language is sort of having that culture of awareness of speaking both in the tongue of data science and of manufacturing or of medicine is very rarely are you going to have the individual, but you'll have the teams that hopefully in the organizations that can speak both of those languages. So I see my time is up, and thank you.